Okay, so here's the first problem set. And again, I'm not going to be picky about knowing the exact human population. You can go out to worldometers, which is where we began in 101 last semester. You can go to worldometers and look those up. And I have a little spreadsheet here that I've been using for a while. This one's for volume. But one thing you might try, and I think of it a lot like, you look in the back of an atlas, and it's got all the cities, listed, and you can look up the distance between two cities. So in this particular spreadsheet, what I've done, if I've got, say the meter here, millimeter, micrometer, nanometer, you can say I'm sort of hopping down one order of magnitude each time. What I've done in this little spot, and here's what I should probably be doing here, is if I start with this is 1, I can just say this equals that number divided by 1,000. And then, so from here I can see that 1 millimeter is 1,000th of a meter. And then I can also see that 1 cubic millimeter is 1/1000th of a meter. But we can do the same thing for energy. So what I suggest doing is coming over here and doing something like this. So joules, calories, BTU, kilowatt, hour, etc. And then over here you can go joules, calories. I'll make this a little bit bigger. BTUs, kilowatt hours. And so obviously these numbers are just 1 along this diagonal. Come here, center that up. Right, 1 calorie is 1 calorie. And then make these your active cells, so just the yellows. And let's see the best way to do this. Oh, let's do it this way. Let's sneak one more row in. So if I put, let's just put 10 calories in here. So now I can look at the conversion between calories and joules. You don't have to do this, but it's a pretty good exercise. I mean, you can just go and look it up in the book too. But I kind of like to use things that I've made myself. So let's go back there. So I thought this was in the book. What is the calorie? What is the joule to calorie conversion? It's 4 point. What is it? 4. Is it 4 point?
4.2 joules.
Okay. Okay. Then how about calories to BTUs? I might go look that one up online.
Yeah.
So I copied that one, and then calories to kilowatt hours. This is kind of wild. You can actually just copy right between Excel. So equals that times that. Nice. Okay. So I'll keep this as my white column, no fill, and then I'll have this as my fill column. There we go. So if that equals 1, and this number equals that number, this is kind of redundant, but times 1. And so I'll just do it just for this 1 calorie, but if I got 20 calories, now I can see that all of those equals that times 1. So you can make your own little spreadsheet like that. Fill it in, then you've got it, save it, use it, and you can do your entire homework problem with one stroke of a key. Right, so you type in, boom, there it is. Yeah, it's nice. And then, and if you felt like it too, you could just take this whole thing, and this will come in handy for summary 3. Like if I take this right now and copy it, if I drop into Microsoft Word, just type in something like question 1, and now if I go up to paste.
Don't you have to paste that as a picture?
Yeah, definitely paste as a picture. You could paste it as Excel, but then Microsoft Word is going to leave that as an active Excel document, and you don't want that. It just gets, rarely do you want to mess around with that. And now you've got it in your Microsoft Word, and then you can save that as a PDF, hand it in, etc. So, okay. Oops. Sorry. I know. I think yeah, no, it was just more trouble than it was worth. All right. So there's problem set 1. We've already covered that. We've looked at Solomon a little bit already, so go ahead and dive into that. And I think Tim already went over the rubric for summaries too, so I think you know what to expect there. That's it. All right. And then most of these, I'll just give you a fair warning. Most of these previous postings are from previous semesters, and we will we'll use them a little bit. Oh yeah, there's that guy right there. Okay. All right. Well, let's go ahead and just start getting through the chapter here, so we can get on to our what we're going to need to know for the exams. And I think we got most of the way through chapter 1 last time. Let's just go ahead and finish off chapter 1. Shouldn't take too long, and then we'll get on with the rest of it. Chapter 1. Okay, so I know we went over this definition of potential energy. We went over the various fractions of where our energy comes from. We then looked at this figure, which I think is just individual renewable. Yeah, and this is just the renewables, and not a whole heck of a lot of change in traditional biomass. The figures that we saw in 101, that's just going to be fairly constant. Hydro might go up a little bit. Geothermal, I think, has the potential to go up tremendously. Solar and wind and wave will definitely increase. I know we're going to get more energy from waste, and I don't know. We'll see what new biomass does, but I'm not holding my breath on that one. Okay, here's the peak oil discussion we had from NRG 101. It's looking that, gosh, if oil is going to maintain its current status, then we're going to have to find new crude oil. If you go back and look at the 101 book, there's a shot of Russia putting its flag in the North Pole. Whether or not it comes to that, we'll see. We did look at the breakdowns last time of how energy is used both by fuel, sector, and end use. Okay, and then here's your UK. Obviously the book is based upon the UK, so this is where their renewables come from. And now, this is pretty encouraging. If you look at the total winds, this has a lot to do with that problem we just did. Total wind is coming online pretty big time, mainly in offshore wind in the UK. There's a shot, if you get a chance, go over to Wally Higgins' office. He shows this pretty massive wind turbine farm offshore in the UK. Landfill gas, looks like it might have peaked. I've heard that Sweden now has to import garbage. They recycle so much. So at some point, I mean, you can only make so much garbage, right? So at some point that's going to sort of peak out. It looks like maybe that has peaked in the UK, at least for the time being. Here's your gigatons per year of emissions. A lot of times people say, well, natural gas is cleaner, but shoot, at the end of the day, when you burn something that has carbon in it, carbon dioxide comes out. You might get a little more bang for your buck in terms of the natural gas, sort of energy per CO2 molecule emitted, but obviously they're all on the rise. And I was a little surprised, but just all of humanity is driving even more. Even in the UK, they're driving their cars way more than they used to. So that's where I think a lot of that oil CO2 emission comes from, transportation sector. And then here's the changes in temperature, going back all the way to 1860. There are some solar events, some volcanic events that affect this. But in general, there's really no question that the average temperature of the atmosphere is increasing, and that seems to be strongly correlated with CO2. And then what we'll know is that that's because CO2 is opaque to a lot of the radiation that's coming back off the planet. And that's the main reason, is that, and we'll look at the spectra in a little more detail when we move through the book, but especially when we get into the section on glass. But thinking about how light and radiation comes through the atmosphere, about 30% of it gets bounced back. But of that penetrates the atmosphere and hits the planet, once that energy has been absorbed, it's going to get re-emitted at a different wavelength. In general, those wavelengths are much longer, and it's the longer wavelengths that CO2 absorbs, right? So every type of matter is one of three things. We'll get into this in more detail. Either it's going to be reflected, transmitted, or absorbed. Those are the only three things that can happen to a photon when it interacts with matter. And if it's being absorbed, it just means it's getting hotter. Just, go stand out in the sun and see if your body is transparent or opaque to the sunlight. If you get hotter, you're opaque. You're absorbing the sunlight. It's pretty simple. And one thing I'm yet to see, the main reason for grabbing that Solomon paper, and maybe I mentioned this last time, I really want to do the experiment. We just got jar of CO2, jar of methane, jar of air, stick them out in the sun, just see which one gets hotter. And that ain't rocket science. It's just that's science. Okay, this number, 5.4 million exajoules. When you run this, I think I've got this on the next page. Here's 5.4 million exajoules. That's what hits the Earth's atmosphere. A fair amount of it gets reflected. 31% just gets reflected back. But we know that we use 500 exajoules per year. So is that good news or bad news? Well, do the math, and that comes out to be 10,000. So that means that we're using 1/10,000th of the energy that the sun supplies. A second ago, we did the wind turbine problem, and I think it comes out to be like each person on the planet needs, 200 people, each person needs 200 turbines. No, it's the other way around. Each turbine could supply enough energy for 200 people. So if you look at this 10,000 to 1 ratio, it means that, well, gosh, we could continue to expand. We could continue to use more energy per capita. The question is, how are you going to get that energy? Is it going to keep setting things on fire? Should we put in more PV, put in more wind? Because we're not at this thing that's called the Kardashev Limit, or a Kardashev Type 1 society yet. That's a civilization that uses all of its sun's incident radiation. We still have room to grow. But what that means is that we'd have to have solar panels across the entire planet. This little bit of math with 3.5 million wind turbines, we only have to give up Montana. If you put a wind turbine on every 5 acres in Montana.
Why does it have to be Montana?
Well, it doesn't have to be the state itself, just something that size.
Let's go get rid of it.
Someone else's back. Oh, Texas, there we go, okay. Okay, that'll work. But that's the ratio where we sit right now in relationship to the photosynthetic ceiling or the Kardashev limit. It's you can think of that in a similar way that we thought of that 10 million to 1 ratio. We're consuming fossil fuels 10 million times faster than they were deposited. It's probably even more than that. I think most of that coal got laid down over the course of a few tens of million years. But this is a number to keep in mind when you look at a figure like this. I'm always astonished. Well, I am. I'm pretty astonished to see how inefficient photosynthesis is. I mean, you're like, oh, solar panels, they're only 10, 15, 20%. Well, gosh, poor photosynthesis, man, it's less than 1%. The other thing to keep in mind here is, so could we just use biomass and satisfy our energy demands? Look at that number, 1260. Could.
We use all of it, or
Use half of it. Yeah, we have to burn half of everything that grows every year to sustain our energy demands. So, if we're going to continue on our energy consumption trajectory, we've got some pretty important decisions to make. Pump storage, I don't know if I told you, maybe I've beaten this horse to death, but there is an 800 megawatt pump storage facility going in right here in Montana. It wasn't because someone just wanted a big puddle of water. It's because somebody wanted to make some money building a wind farm and selling the electricity. Well, that wasn't going to work because we can't get electricity out of the state quickly enough. So in tandem with the wind turbine farm, we're building this 800 megawatt facility, which is huge. California is going to try to get to 1.3 gigawatts of storage. And when I say that, when I say gigawatts in storage, you might scratch your head a little bit and say, well, you don't store power, you don't store watts, you store energy, right? Well, what that means is that that facility can absorb energy at that rate. It can absorb 800 megawatts. Or in California, they can absorb 1.3 gigawatts with whatever, hydrogen, battery, pump storage, what have you. So storage, strangely enough, is measured in watts as well as joules. But there's your energy security right there, sitting right, gravity. Gravity's not going away. Okay. Now, this guy takes a little closer look at scenarios. This is scenarios from the UK Committee on Climate Change illustrating the potential contribution of renewables to UK in heat, which is, it's labeled here, that's the H, electricity, and transport. The heat is, and you can think of these in terms of locality, like the heat is sort of like here in the room, right? You're going to set something on fire and burn it. You're not going to run around with that heat. The electricity, well, that's, somewhat regional, distributed, grid-like, and you can't run your extension cord to your car. And transport is everything that's moving around, right? Because you're not going to, I guess you've got a fire in your engine if you have a combustion automobile, but that's not conventional heat. So if we look, what we're seeing right now is that 6.6% of electricity in the UK is made from renewable sources. Moving forward in the future, here's a 2020, and they've got, 4 different 2030 scenarios, each one slightly more aggressive than the next. I really like this renewable heat deal myself. I would love to put in seasonal heating in my house. We'll do the math here in a little bit, but as it turns out, if you buy your neighbor's house or buy a foreclosed house, there's enough volume inside that house to store all of your heat for the year. It turns out to be about a 1-to-1 ratio. If I were, all summer long just banking all this extra heat that's bouncing off my house that I don't want, putting that into hot, insulated hot water in my neighbor's house, I'd have a nice house next door, right about close to boiling, 212 Fahrenheit, 100 Celsius. You wouldn't want to boil it off because you're dealing with pressure and all that, but nice big juicy ball of heat next door that I could tap off and just about make it through the winter. And the same was true. I could buy the other neighbor's house next door and start banking ice all winter, and then I could use that for my fridge and my air conditioning. So it turns out, and so right now they're sort of showing these numbers at 12%, 35, up to 50. I mean that's really what that is. That's kind of some of it's cogen, some of it's burning gas or burning waste to get your heat from a renewable source. But you could also think of heat as a year-round renewable bank. Not that easy to store heat, right? It's always kind of leaking out and wanting to go elsewhere. But that's a thought going forward for how you can do a little more year-round. If you take Jonathan Bowes' geothermal class, you might get into that in some of those numbers a little bit too. All right, let's take a break there, and then we'll start digging into chapter 2. But I like chapter 1. It's a nice overview of the renewables.